So we're going to look at a few different scenarios here where they tell us information about the graph and how the derivative's behaving, how the second derivative is behaving, and how that can get us a sketch of a function. So we have some scenarios. This first one deals with the first derivative. The second one kind of mixes first and second. And then this one just gives us a function. But what I'll do is I'll go through and talk about these kind of key values that we can grab that will help us make the graph. And actually in our participation and written assignment, I even provide the list of things that we go through. So when we get to that question, I'll try to pull that up from memory of all those different values we want to look at. All right, so given f prime of x is more than 0, and what helps me is when I see that the derivative function is more than 0, that means we're increasing. So again, first derivative tells us about increasing, decreasing. So given that we're increasing on negative infinity to negative 4 and 2 to infinity, and then f prime of x is negative, which tells me we're decreasing on the interval negative 4 to 2. With that, we're going to sketch the function. So not a ton of information, but enough to get a sketch going. So what I want to do is I just kind of want to visualize my cutoff values. So trend is going to change at negative 4, and then negative 4 to positive 2, and then positive 2 to infinity. And it's going to be over here we're increasing, and then we're decreasing, and then we're increasing. I'm just going to do sketch off to the side. So increasing, changing to decreasing, changing to increasing. All right, so I want something that looks like that. So it looks like I'll have like a relative maximum and relative minimum. And with that, these turning points should be happening at basically what I highlighted. So at that negative 4 and positive 2, that's where we're switching trends. So I'm just going to mark some points. I have no information in terms of exactly where coordinates are, but I just want to get these kind of trends. So how about a big value there, a low value there, and we'll see how best I can connect these dots. So I'm going to go up and hit that peak, and then down and hit that valley, and then go off to positive infinity. And we're going down to negative infinity on that left-hand side. So reading left to right, increasing, then decreasing, then increasing, with those trends changing at negative 4 and positive 2. All right. F of x is increasing and concave up. So concave up looks like that on negative infinity to 0. Then f of x is increasing and concave down, which looks like that, on 0 to infinity. Sorry, my brain stopped for a second there. Okay, sketch the graph. All right, so our dividing value here is going to be at x equals 0. So to the left, we have increasing and concave up. So if I look at my concave up, which goes down and then goes up, there's two parts to this. So there's the decreasing, and then it switches to increasing. And we specifically want the increasing part. So really, I just want to work with this half where it's concave up and increasing. So over on this left-hand side from negative infinity to positive infinity, I should be seeing something with that shape, where it's kind of curving upward and it's increasing in nature. Then the other half of the graph is concave down, so that opens downward, and is increasing. So again, this graph has two pieces to it. It increases and then decreases. So what we're going to have is this increasing side, which is over here. So when we get over here, should be increasing. So what's happening is we are switching from concave up to concave down. So what that's telling me is at x equals 0, there's an inflection point. So we're switching concavity. What it's going to look like when I connect these two graphs together is something like this, where it's curving up and increasing, and still increasing, but starts curving down. And that's the only behavior that we have. I'm just going to go ahead and have the inflection point at the origin. It's not so easy to see there. And let's go ahead and grab this curvature, and then it's going to kind of switch to curving down. Something like that. Basically looks like an S, just a less curvy S, but making sure that that's concave up, concave down, and increasing all over. All right, our last one here. We have this function f of x equals x to the 2/3, and what we're going to go ahead and do is look at the first derivative and second derivative. So some pieces we're going to look at, and like I said, with our participation and written assignment, there's even a list. We're going to start with the intercepts, and then we'll take a look at critical values. Oh, I'm just going to make a note to the side here and we'll go through it. Intercepts, critical values. We'll talk about increasing, decreasing. We'll talk about inflection points. We'll talk about concavity, concave up, concave down, and then relative minimums and maximums. Okay, that's a lot, but a lot of this ties together, so hopefully it won't be too bad. Okay, intercepts is where we plug in x equals 0 and y equals 0. So to get the intercepts out, if I plug in x equals 0, so 0 to the 2/3 is just 0, so that would be 0, 0. And actually, that would be the y-intercept too, so that's all done. Nice and easy there. All right, so with that, we have a coordinate to graph. We're graphing at 0, 0. Let's go ahead and look at the critical values. So what we're going to do is take the derivative. So f prime of x is equal to 2/3. X to the 2/3 minus 1, which would be a negative 1/3. So that is, let's go ahead and set this equal to 0. 0 equals 2, and then I'm going to have this as 2 over 3 times, I'm going to change this to radical form, so this is the third root of x. And let's see what we can do here. Really not much, because if I multiply both sides by that cube root of x, it turns into a 0, and it all just wipes out. So there are no critical values. Oh, shouldn't cross all of that out because that first derivative is going to be helpful. But no critical values, so that basically tells me there aren't going to be any relative minimum or maximum values. But let's go ahead and think about increasing, decreasing. And really, if there aren't any relative minimum or maximum values, the trend isn't going to change. So it should just be a single trend over the whole graph, which means we can just choose a value and plug it in here and see what happens. I do not want to plug in 0 because then I'd have 0 in the denominator and that doesn't help. So I'm going to go ahead and plug in a 1 because that's a nice one to take a weird exponent of. So that just turns into a 1, so that's a positive 2/3. So that tells me that we're increasing everywhere because that derivative would be positive. So we're increasing from negative infinity to positive infinity. And I immediately want to take that back. I'm sorry. It's one of those moments. I need to erase that. So there were no critical values here, but I actually kind of whispered-ish something to myself that was actually very important, which was the idea that we can't plug in 0 here. So there's actually a spot where our derivative is undefined, and that's important. So, knowing that x cannot equal 0, we want to take a look at that. So let's take a look at our first derivative test using these intervals from negative infinity to 0 and then 0 to infinity, where we're grabbing that 0 not from solving this, but rather knowing where our derivative is undefined, because those are important values too. So if we do our first derivative test with this, so let's go ahead and do -1 and +1 using our first derivative function of 2/3. Let's go with 2 over 3 cube root of x. So if we plug in -1, that's going to be a -1. So that'll be a -2/3. So we're seeing decreasing over there. If we plug in +1, cube root of +1 is +1, so +2/3. So we're seeing increasing. And that's where we get a change in trend. So critical values, we're seeing x equals 0 as a critical value. It's just a special one where our derivative is undefined. So with that, we get increasing is occurring from 0 to infinity. So on this part of our graph, we're seeing increasing, and on the other side of our graph is decreasing from negative infinity to 0. All right, I just want to make a note. Over here, we're decreasing. Okay, so over there, it's going down. Over here, it's going up. And then at x equals 0, it's not going to be a nice minimum or maximum value like we've been seeing. Typically, what will happen here is either this could be an asymptote in the graph or a sharp corner, which is going to be the sharp corner that we see here. And that's because we could plug in 0 here. Plugging in 0 there is fine. It's just when we get to taking the derivative that's putting x in the denominator, and we don't want that. All right, so the intercepts gave us a coordinate, and they can give you more coordinates than just one. It was just in this case, running the first derivative test, getting the critical value. Now we have increasing, decreasing. So let's see, we did that, we did that, we did that. Inflection points, so that's where we would take the second derivative. So let's see, 2/3 times -2/3 would be a -2/9. And then x to the -1/3 minus 3/3, so -4/3. So we're basically going to run into the same issue here. Let's see, if we do this, it would be -2 over 9, and then cube root of x to the 4th. So if we try to solve that for 0, we're going to have issues, but we want to keep in mind that x cannot equal 0, which would throw us back to our first derivative test. And actually, since I want to determine, so first of all, there's no inflection points. That's what we're getting from this, because if I plug in 0, it's the same thing that happened right here. So if I plug in 0, everything wipes out. So there's no inflection points coming from that. But I'm going to use the fact that I can't plug in 0 there. So x equals 0 is something that we're interested in. So in terms of concavity, what we could be seeing is that, let's see, we're undefined at 0, so that could be a spot where we're switching. So I'm going to set up a similar table where over here we were evaluating the first derivative of x. I'm going to do the same thing, that there could be some concavity from -infinity to 0 and then 0 to infinity. I'm just going to use those same test points, but now I'm going to look at the second derivative. So if I plug in -1 there, because of that exponent of 4, that'll turn positive, And let's see, that'll be a negative 2/9, that'll be negative. So this is negative, concave down. And then if I plug in positive 1, we're going to get the same thing, negative, concave down. So there's our, no inflection points, but we have a critical value that we need to look at because of where the function's undefined. Concavity we found. So with that, overall this graph is concave down for both of these sections, but notice that it changes in terms of the increasing versus decreasing. So decreasing concave down looks like this, increasing looks like this. So with that, I kind of want to put those two shapes together. And what we're going to do is it's going to switch at that 0, 0. And like I was saying, with our derivative being undefined there, what we'll have is a sharp corner. So what we should be having is something that decreases down there and then increases up over there. And there's a sketch of our graph. That was a messy one, but it's good to look at these messy ones together. Some of these, you'll have these nice critical values, and that'll set up your intervals to work with. But going through these, and then what we can see from the graph is this would be a minimum value at 0, 0. So we would have a relative minimum at 0, 0. It would in fact even be an absolute minimum. No relative maximums though, since it goes off to positive infinity on either side. When we get to the end of this, what you can do is always graph it to double check. So x to the 2/3 there to see that we did it right. But that's how we can put these pieces together. So again, it was intercepts, looking for critical values, using those to find increasing, decreasing. Then from there, looking for inflection points to set up those intervals so you can describe concave up or concave down. For us, our interval, it was concave down. At x equals 0, there's technically no concavity, so how I would write the interval for concave down would be negative infinity to 0, union 0 to infinity using parentheses, because at x equals 0, there technically isn't concavity. And then, let's see. So that gave us our graph, and then we could see from the graph that relative minimum.